if we go back to the previous example we just worked through, and this was the distance or displacement in meters, S is in meters, at any given time t. And when we graphed this, which was way back, we graphed it over the first 4 seconds, and this was the distance in meters or displacement. Okay. So in the previous little video, we found that ds dt, and we worked it out from first principles that it was 4t. Now what is that? ds dt, we've said that the derivative is the rate of change of one quantity with respect to another. Here it's a rate of change of distance in meters with respect to time, which is in seconds. So if you like, if you look at ds dt, it's a way of looking at what happens when you divide distance by time. So ds dt is the rate of change of distance with respect to time. So that is equal to speed, or maybe in velocity if we're talking vectors and stuff. So ds dt being 4t is the speed. Now we said that it's not average. The derivative is the instantaneous rate of change. So the derivative is the instantaneous rate of change. What do we mean by instantaneous? That means at any particular instant we can work out the rate of change, and the rate of change in this case was speed. Now other different scenarios may be flow rate of liquids or temperature rise or whatever it may be. So we're here talking about an example with distance and time, so the instantaneous rate of change we call speed. Now that means that at any point along that curve I can work out I can work out what the gradient is of that curve, and so knowing what the gradient is, I can work out what the speed is. So when t equals 3 ds dt, sometimes you could write it like that. So ds dt when t is equal to 3, you simply just substitute in the value for t, so it'll be 4 times 3 equals 12. In this case it'll be meters per second. When t equals 4 ds dt, t equals 4 equals 4 times 4 equals 16 meters per second. All right. Another way to look at it is if I was to draw the tangent at 4. So given that this curve here is going to rise quite steeply, that might be the tangent. 16 is the rise divided by the run, if that is the tangent at that point there when t is equal to 4. So that rise divided by that run would be equal to 16 at that point. At t equals 3, rise over run would be equal to 12, and so on. So there is a meaning and an application of the derivative. We worked out from first principles that the derivative of ds dt when s of t is equal to 2t squared plus 3 is equal to 4t. And in this case we had a distance time model going on, so the rate of change of distance over time is equal to speed. So the powerful thing about this is that this allows us to work out not just any whole number, but at 1.3 we can work out what the speed was. 3 point, or it's not just restricted to here, if this was over a bigger domain, we could work out at any time t what the speed was.